Hello guys, I'm back. My name is Jeferson Costa. I'm a chemical process engineer with expertise in plant design, and today I will talk to you about Aspen Hysys dynamic simulation. And to do that, I will give you some basic understanding about the dynamic simulation and do an example with you. Before I start, let me give you two advices. The first one is that this presentation as well as the process simulation I do during this video is available for my students at my Aspen Hysys Applied to Plant Design, so you can download it from the student area. And if you are not a student of mine, you can have this presentation if you help me to reach 100 likes to this video. So you just need to give your like, share this video, and go to my website jeffersoncosta.com and look for in process, and there you will find the link to join my Telegram channel. And besides that, you will find a link for my YouTube, for my LinkedIn, and also to my fan page in Facebook. Moreover, you will have access to my blog where I have much more content about chemical process engineering and plant design. Enough talking, let's go to our presentation. Dynamics is an advanced tool in process simulation, and with that we get our steady-state process model and convert that to time-dependent process. It means that instead of having only the instantaneous results from the steady state, we can change parameters to see how is the response of our process during a period of time. And more, with that we can evaluate the control systems, assess process safety conditions, and do a better startup plan, verify shutdowns conditions, emergencies, and consider many other scenarios and troubleshooting before you go to the field, or if you are already in the field or working in an existing industrial plant, you can verify those issues without shut down your plant. However, before starting a dynamic simulation, you need to know some things about that. The first one is that you need to know how to do a steady state simulation, and that must be very clear to you. How do you convert that? How do you solve issues related to steady state simulation? Because you will not be able to start your dynamic simulation if your steady state simulation is not converted. So my suggestion to you is that before you start learning about dynamic simulation, you should master steady state simulation for piping systems, rotating equipment, heat transfer equipment, separation units, columns, and reactors at least. And after you have mastered all of this, you should try learning about dynamic simulation. But it is not enough. To do a dynamic simulation, you need to know the basics about control system, and I will talk a little bit about that in this presentation, but I don't have any commitment to get deeper in this subject, only the strictly necessary to know how to do your first dynamic simulation. And finally, to do a dynamic simulation, you need to know what you want to evaluate, because the main reason for a dynamic simulation is to verify or evaluate disturbance in your system, and to do that you need to know what you want to evaluate. So if you lack any one of these three conditions, you may be able to do a dynamic simulation, which I will show you here. However, your understanding will be very limited because of that. As I mentioned to you before, to start your simulation, you need to have a steady state simulation converted, and in this presentation, I have a block flow diagram with a system and with information enough to you build and convert your process simulation. I will not do that step by step, but with the block flow diagram, if you already know how to do your steady state simulation, you will be able to do that. And what I will focus on in this presentation is about the control system. And to talk about the basics, I need to tell you about the two kinds of actions in our controller. The first one is the direct action, and it means that we have a set point, and if to increase the present value, we need to increase the valve opening, we are talking about direct action. On the other hand, the inverse action is the opposite. If to increase the present value, we need to decrease the valve opening, we have an inverse action. I will get more details when we talk about the block flow diagram, but keep in your mind that when I need to increase the present value and I need to open the valve, I have direct action. And if I need to increase the present value and I need to close the valve, I have the inverse action. And that is very important because to set your control loop, you need to define if the action in your control system is direct or inverse. And in this presentation, we will set a control loop and we will verify what happens with our control if we change the process conditions for the cold water to 3.5 bar G and 10 Celsius. Here you can see our block flow diagram. It is not a pipe instrumentation diagram and it is not also a process flow diagram. It is a mix of them and it is just to exemplify our process and to make it easy to you build your process simulation in steady state condition and convert that to the dynamic mode. And what we have here is a cold water that needs to have its temperature increased to 60 Celsius degree. So we have a heat exchanger HX100 that we supply with saturated steam at 9.3 bar G, and we have condensate at the outlet of the shell side, and the TV breaks the pressure of this condensate to 7.3 bar G. We have other information here about the heat exchanger, that is the allowable pressure drop in the shell. It is 0.1 bar, and we have also the allowable pressure drop in the tube, and it is 0.35 bar. Besides that, we have the representation of a temperature elemento here that is associated with a temperature indicator transmitter. So it means that in the field, the operator is able to read the temperature values, and this transmitter sends the signal to the control room, where we have in our supervisory a temperature indicator controller. So the operator can see also in the control room, in the screen of operation, the values of temperature measured in the field, and this controller is a reverse action that sends the signal for the control valve. And this is reverse because, and the action is reversed because if the present value decreases from 60, I need to open the valve to return the value to 60. On the other hand, if the temperature increases from 60, I need to close the valve to return the value to 60. So there is an inverse relation between the present value behavior and the valve opening action. You will be able to observe that during the dynamic mode. Don't worry about that right now. So let's go to Aspen Hysys and see how to build your first dynamic process simulation. So guys, we are in the Aspen Hysys, and you can see that I already have a converted steady state simulation in my screen. And based on the block flow diagram, you can do the same, and I will just give you some advices here that you need to complete or set your steady state simulation to convert that to dynamic mode. The first thing is that you need to specify the valves that you have in your simulation. And that is important because when you go to dynamic mode, Aspen Hysys will do calculation related to flow based on the pressure drop from a point to another. So to do that, you can go to the valve and go in rating and specify the settings for your valve. In this case, I have two manual valves here, and what I want from these valves is that they operate 100% open. So I will choose 100% open, and when I click on valve size, Aspen Hysys will calculate your CV or your CG depending on your choice. I will do the same for this hand valve, and I want this 100% open with the minimum of pressure drop on this because this valve is not for controlling, and there is already a pre-calculation done by Aspen Hysys. I will just click on valve size to fix that, and you will need to do the same for the control valve you have in your system. And this one is the most important valve in this simulation because according to the opening and closing of the temperature valve, your flow will increase or decrease to guarantee the temperature set point at the hot water. As standard, Aspen Hysys considers a valve opening of 50%, and I will let that as it is, and we need to inform the pressure drop. So to reach my 7.3 bar-G at the condensate side, I have this pressure drop, and I will do the valve size, and I have the CV for this valve. This way we are working with theoretical valves. That is not the best way to do that because when you are doing a dynamic simulation, you want to have the most accurate results compared to the field application. So what best fits for dynamic mode is getting the field information. So in this case, you need to go to the control valve datasheet and verify the CV and add to your process simulation. The same for heat exchanger. Here I simulated theoretical or for the example heat exchanger, but the best results that you can have in your dynamic simulation is getting real information from equipment and adding that to your process simulation. In this way, you will be able to compare the results from your process simulation to the results that you have in the field. And once you validate that, you can do disturbance in your system to verify what would be the responses if you have those disturbances in your process. And now I will add the controller to our control valve, and to do that you go to model palette and look for the PID controller. I'll click on that, and doing double clicking I can access the submenu, and here we will choose the variable that you want to control, and in this case is hot water temperature. So we need to look for the hot water and set the temperature. And this information will go to the controller that will send a signal to a control valve, and in this case is the valve 102. This signal goes to the actuator, and depending on the present value, the controller will require that the control valve opens more or closes more to reach the present value set point. You have the option to set a remote set point. I will not do that because we will set the set point inside the controller. And to do that, we go to parameters and we need to give this information to the controller. So the first thing I will do is inform the present value range from my process. It is the minimum and the maximum expected conditions that I have in my process. So as a minimum, I will inform 10, and as a maximum, I will inform 100. Besides that, I need to inform the PID controller parameters, and I will start with 0.5, 1, and you can let the differential part as empty, or you can add a value to help you in your tuning control. Most of the process doesn't need the derivative, but I will not get in details about that, but at least the key C and TI you need to have in your PID controller. And now I will need to choose the action in my valve, and just to revise that, I want to set my hot water temperature at 60 Celsius degrees. So if this temperature increases above the 60, I will want to close the valve. I want to close the valve because with that I will have less mass flow passing through the valve, and with less mass flow I will have less heat exchanging, and because of that my temperature will return to 60. On the other hand, if my hot water temperature decreases, I need that my valve increases its opening because I need more flow through the heat exchanger in a way that I have more heat exchanging, and that will result in a high temperature in the hot water, and I will get closer to my set point. So in this way, what I have here is a reverse action in my controller. When the present value goes down, I need the valve opening to goes up, and when the present value goes up, I need to the valve opening goes down, in order that I always get the temperature set point of my present value. And the standard choice of Aspen Hysys is reverse, so you need to take care about that if your control loop is a direct action. And finally, I will need to change the mode from manual to auto, because this way the Aspen Hysys will do calculation and the controller will ask my valve to open and close automatically. If I let that in manual, it will be a fixed opening to the control valve, and we have this mode auto and manual in the field. It is very common, and the execution will let it as internal because all the calculations are done in Aspen Hysys. That said, you can close this window, and now I need to set to Aspen Hysys what will be the sets of my streams. What that means? When I do a double click in the stream, I have the tab Dynamics, and I have two kinds of sets or specification to inform to Aspen Hysys. I can set the pressure specification and I can set the flow specification. Once I do that, this value will not change, this value will not change, and the flow will be the results from the pressure drop calculation. So in this case, I will let all of my streams as the pressure specification activated, and I will do that because those are information from my system. And you can verify that the dynamic specification is related to the degree of freedom of your system. For instance, when I go to the stream, you can see that I set the pressure for the steady state calculation, and according to others information in the process simulation, the Aspen Hysys calculated the flow. So flow is not activated here because it was an indirect result from the process simulation. On the other hand, the cold water, it is a stream that is fully specified by me, and we have the flow activated. I will deactivate that because now I want Aspen Hysys to do the calculation related to flow. And you need to verify the others also. And you can see that the hot water is a result of all others specification in our calculation. However, I will set pressure as activated to Aspen Hysys identify that the flow needs to be calculated according to pressure drop, and the same for the condensate. I need to verify that and activate pressure to set the pressure fixed as the control valve open or closes during the dynamic simulation. Once you have your steady state simulation converted, you have the valves specified and you have your streams specified also in dynamic mode, and you can see that I specify only the inlets and the outlets of our process simulation. I will not change anything inside this because the valves here is the boundaries of my process simulation. So I only set what is going in and what is going out. I didn't add a manual valve to hot water because I don't have any specific requirements for the hot water pressure. So because of that, I don't have manual valve. If I added a manual valve there, I needed to set the pressure downstream of the valve. So I will not do that. And finally, we can go to the dynamics and you look for the dynamics tab, and there you will click in the dynamic mode. The first time you do that, Aspen Hysys will ask you if the dynamic assistance do a verification in your settings, and I will do that. And it may give you some advices, and you need to read the advices and verify if you agree or not. In this case, I will accept them, and now I will finish. And finally, I return to dynamic mode and I will click on yes. And now we are in the dynamic mode, and that means that I'm not free to do many changes in the steady state conditions of the equipment. For instance, all the information related to shell and tube heat exchanger is now fixed. I cannot change that during the dynamic mode, and that is not a problem. And before running my simulation, I will add the faceplate to the screen, because with that it is easier to us identify if the valve is opening, if it's closing, and how is the behavior of our system. So once I hit on run, Aspen Hysys will start doing the process simulation, and as our present value is with the same values of our set point, I don't expect to have too much changes in our simulation right now. So let's verify. And you can see that it is working because the OP of the valve changed, and also I have a little changing in my mass flow. But as I told you, I didn't expect too much changes. To make it easier to us understand the behavior of our system, we can add some charts to our process simulation. And to do that, there are many ways, but what I will do is click on the controller and go to the chip chart tab, and there I will choose information related to set point, present value, and output value. With that, you click on create strip chart and display. And now I have a chart that shows me the behavior of our control system. And to do some verification, we can change the controller set point. So to verify the control loop, I can go to my controller and change the set point, and we'll verify how is the behavior of our system based on this modification. So I will change that to 50, and you can see that my valve changed its opening. Now it's around 30%, and if I return to 60, it returned to its position, and because of that we have changes in steam flow. Let's do the changes again and take a look at the mass flow in the stream. So when I decrease the set point to 50 Celsius degree, it means that our present value is above our set point. In this way, I need to close the control valve. Let's take a look. The valve closes, and because of that, the pressure drop in the valve changes, and now I have a flow around 400 kilometers per hour. So it is the way that a control valve works in the field, and that is what Aspen Hysys does in simulation. And now I will return my set point to 60. And now that I have my dynamic mode running as expected, I do a change in my cold water inlet conditions in order to evaluate if my system is able to respond to this disturbance. So the main concern related to dynamic mode is to evaluate if changes in your process will give you the results that you expected. And now I will change the cold water pressure, and it means that as my pressure increases and I have a fixed opening to the manual valve, Aspen Hysys will identify that the mass flow is increasing also. So my first approach will be to change the cold water pressure. And with that, you can see that the mass flow increased. And now I can see that the control valve went to the full opening. However, it is not enough to bring my hot water set point to 60, because once you have a CV calculated and specified in your valve, it means that you add to your valve a flow limitation. And if in my process the cold water temperature decreases, it will get worse to my process because I don't have enough steam, and you can see that the hot water decreases more and my control valve is 100% open, but I don't have enough steam to heat up the hot water. In this case, my first approach should be to do a new specification for the control valve, and to do that I need to stop my dynamic simulation and work in the steady state condition. So that's why it's so important to master steady state condition before you go to dynamic mode. And moreover, I need to verify also the heat exchanger to see if the heat exchanger is able to handle the new values of flow. That is not the purpose of this video, and of course that there are many other features that Aspen Hysys gives to you. We can accelerate or deaccelerate the chart time. We can do other charts relating other variables to our process simulation and many other things that you will find once you get deeper in dynamic mode in Aspen Hysys or also in Unison Design. So this is it, my friend. If you want to get this presentation PDF, you can help this video reach 100 likes in YouTube, or if you are a student of my Aspen Hysys Applied to Plan Design, you can download that right now from the student area. I hope you like it, and I'll see you soon in the next video.